Imagine how the universe operates. The balance, the precision, the laws that govern everything from the spin of a planet to the energy that fuels a star. How does it all hold together? The key, my friends, lies in a concept we call symmetries. And these symmetries aren't just fascinating, they're fundamental. They're the reason why certain physical quantities, such as energy, momentum, and angular momentum, always stay the same. They help us understand the behavior of Earth as it gracefully orbits the Sun, not simply as an object pulled by gravity, but as a traveler navigating the curves of a space influenced by the Sun itself. But this is just scratching the surface. There's a theorem, a principle, if you will, that binds all of this together. It goes back to 1918, and it's the work of a brilliant mathematician. It reveals astonishing connections and implications for our understanding of the universe. But there's a catch, a twist that might make you rethink what you know about conservation laws and their boundaries. What's the twist? It's too soon to tell. You'll have to stick around to find out. What's up, my amazing and curious folks? Ready to unravel mysteries together? I'm your host, Caesar, and with me is the ever-insightful Sonia Guimaraes.
Hey there, everyone. So glad to be here. We're going to dive deep into some fascinating stuff today.
That's right. And if you love embarking on this journey of discovery with us, don't forget to subscribe to our channel and hit that bell icon so you won't miss any of our episodes. This is the Curiosity Wonderland, and we're just getting started. So, to further delve into the intriguing world of symmetries and conservation laws, let's look into a question that was raised by someone called Kaleberg. He asked, doesn't spatial invariance imply conservation of momentum, and doesn't time invariance imply conservation of energy? Indeed, these are some of the profound connections we find in physics, deeply ingrained in what we call Noether's theorem.
Hold up. Before we go any further, can you give a quick rundown on what spatial and time invariance mean?
Absolutely. Spatial invariance refers to the idea that the laws of physics don't change based on where you are in space. You can think of it like this. Gravity works the same whether you're in New York or in Tokyo. This is conservation of momentum. Now, time invariance, on the other hand, means the laws of physics don't change as time passes. It's like the way an apple falls from a tree. Whether it's happening today, tomorrow, or 100 years from now, the apple will fall in the same way. This is conservation of energy.
Okay, that's making sense, but can we put this into some real-world examples?
Sure, let's use a playground. The swing set is a great example of conservation of momentum. No matter how high you swing, you always come back to the same lowest point. That's spatial invariance. The conservation of energy can be seen in a battery-operated toy car. You charge the battery and it powers the car. The energy from the battery is transferred to the car, but the total energy remains the same over time. That's time invariance.
That clears things up. Thanks.
So, in the summer of 1918, a remarkable event occurred that catapulted our understanding of symmetries and conservation laws forward. A young woman named Emmy Noether, who couldn't present her theorems due to her age and gender, had her work presented by the noted mathematician Felix Klein. Her two theorems, which were first published in 1915, were groundbreaking.
Oh, what did they show?
Noether's theorems established that for any physical system, if there are equal and opposite forces at play, and the system's action has a differentiable symmetry, then every independent differentiable symmetry that the system possesses will also lead to an associated conservation law.
That sounds fascinating, but can you break it down for me in simpler terms?
Absolutely. Simply put, if you have a physical symmetry in your system, then there's something about your system that will be conserved. Let's see. An easy example would be if your system is symmetric under rotations, then angular momentum should be conserved.
I see. Any other examples?
Definitely. If your system is identical now to how it was in the past, or how it will be in the future, it's considered to be time translation invariant. This leads to the law of conservation of energy. If your system is identical here to how it was somewhere else, or will be somewhere else, it's space translation invariant, which leads to the law of conservation of momentum. And if your system is invariant under boosts, meaning velocity transformations, it leads to the conservation of four momentum, the center of mass theorem.
That's a lot to digest, but it's starting to make sense. So these symmetries have profound implications for our understanding of the universe, right?
Exactly. Different frames of reference, including different positions and motions, would see different laws of physics if a theory isn't relativistically invariant. So these symmetries and conservation laws are crucial for our understanding of the universe. To further illustrate the importance of symmetries, let's delve into the concept of boosts or velocity transformations. When a theory is invariant under these transformations, we say it has Lorentz invariance. This invariance conserves a symmetry known as CPT symmetry.
Wait, CPT symmetry, what does that mean?
C, P, and T stand for charge, parity, and time. Although these can all be violated individually, together they form a symmetry that is conserved in any Lorentz invariant system.
Interesting. And what about the time translation invariant aspect you mentioned earlier?
This aspect played a significant role in the understanding of energy conservation. For centuries, many of the rules of mechanics were derived through trial and error. The concept of energy, including potential and kinetic energy, was only notable because of how useful it was.
So there was no fundamental reason that energy should be conserved.
Correct. It was observed that energy can neither be created nor destroyed. It can only change form. But with Noether's theorem, this empirical law suddenly had a basis in symmetry. If a system is the same in the past as it is in the present and future, then the conservation of energy emerges as an unavoidable consequence.
Wow. So these symmetries are not just theoretical aspects, but have real observable effects.
Absolutely. A great example of symmetry in action was the 1957 Nobel Prize in Physics, which was awarded for the discovery of parity violation in weak interactions. This is a mirror symmetry known as p-symmetry, which holds for all strong electromagnetic and gravitational interactions. These symmetries ultimately shape our understanding of the universe. Among mathematicians and physicists, Noether's theorem was highly appreciated for its profound implications. To quote group theorist physicist, the principle of conservation of energy was initially shrouded in mystery. However, Noether's theorem provided a mathematical formulation that demystified physics to a significant degree.
Could you give an example of how it demystified physics?
Of course. Let's take the example of classical electromagnetism. We have the electric and magnetic fields, and also electric and magnetic potentials. The fields alone don't fully describe the system, and the potentials contain redundancies. Yet, thanks to these redundancies, there is the freedom to choose a gauge without losing any information about the system.
And I guess this is where Noether's theorem comes in.
Exactly. Noether's theorem implies that if there is an invariance, in this case a gauge invariance, a conserved quantity must be associated with it. As Hermann Weyl first recognized, that conserved quantity is the electric charge.
Wow, it's surprising how much we owe to these mathematical concepts.
Indeed. Beyond that, Noether's theorem also allows us to go a level deeper. If a theory must conserve a certain quantity to be valid, it implies the theory must also preserve an associated symmetry or invariance. The theorem also suggests that if a theory has an internal symmetry, it can generate interactions, a concept that forms the basis of Yang-Mills theory.
So, Noether's theorem is not just about conservation laws, but also about the interactions between particles.
Precisely. It's an all-encompassing theorem that unifies our understanding of conservation laws, symmetries, and interactions in the universe. It's truly profound. Building on the idea of symmetries and interactions, theories like quantum chromodynamics and electroweak theory were developed. These theories explain strong interactions and the electroweak interaction, respectively, using similar symmetry and interaction rules.
So symmetries and invariances are the underlying principles for these theories.
Yes, exactly. For instance, the idea of the electroweak interaction comes from a hidden gauge symmetry that underlies the electroweak theory. However, using symmetries to develop these theories also has its pitfalls.
What kind of pitfalls are we talking about here?
The first pitfall is the temptation to impose additional symmetries or invariances to enable new interactions or to conserve quantities that may not be conserved in nature. For example, there's a theorem known as the Coleman-Mandula theorem that ensures that all of the charges associated with internal symmetries remain unchanged regardless of how you transform them.
So it's like we can't force symmetries into places they don't belong.
Precisely. For instance, quarks have flavor symmetries and spin symmetries, but we can't mix them together.
That's interesting. So there are rules and limits to these symmetries and theories.
Definitely. We have to remember that our universe is fundamentally asymmetric in many important ways. For example, the concept of supersymmetry, which tries to mix space-time symmetries with internal symmetries, is very tempting, but it has yet to have its new predictions confirmed by experiment. So while exploring new ideas and theories, we need to keep our feet firmly grounded in the observed realities of our universe. Let's delve a bit deeper into symmetries. Some symmetries only apply under certain interactions or circumstances. This means that sometimes what we think of as conservation laws can be violated.
That's surprising. Can you give an example?
Absolutely. In particle physics, we consider three discrete symmetries as crucial. The first is charge conjugation, or C, which involves replacing every particle in a system with its antimatter counterpart. The second is parity, or P, where every particle in interaction is replaced with its mirror image counterpart. The third is time reversal symmetry, or T, which states that the laws of physics affecting particle interactions should behave the same whether you run the clock forward or backward in time.
So all physical interactions should respect these symmetries.
That's correct, but there is an exception. The gravitational interaction, the electromagnetic interaction, and the strong nuclear interaction all obey each of these symmetries individually as well as in combination. However, the weak nuclear force violates each of these symmetries individually and in combinations of two. But with all three combined, we find that CPT is conserved under all interactions.
Interesting. And how does this apply to the universe as a whole?
Great question. In the context of general relativity, it's found that the conservation of energy, which comes from time translation invariance, only persists in static spacetimes. For example, this applies in the spacetime describing a non-rotating black hole. However, in the expanding universe, which is a non-static spacetime, this symmetry or invariance does not exist, meaning the associated conserved quantity, which is energy, is not conserved. It's yet another example of the subtle complexities and the fascinating nature of our universe. Let's picture this. Imagine a photon of light being emitted by one galaxy and heading towards another. In a static and unchanging spacetime, the light just travels from point A to point B with its energy staying constant. But in our real universe, the space between galaxies expands over time.
And what happens to the photon in this expanding universe?
As the photon journeys through space, its wavelength gets stretched to longer wavelengths due to the expanding space, causing it to lose energy. That energy doesn't disappear. Rather, because we don't have time translation invariance, there's no law requiring energy conservation in an expanding universe.
So essentially, our understanding of conservation laws has had to evolve.
Exactly. For centuries, it was assumed that conservation laws were fundamental and were identified empirically through phenomenological discovery. But then came Emmy Noether, who proved that there's a powerful relationship between all conservation laws and the symmetries that directly lead to them. Thanks to her, we know that if a symmetry or invariance exists, a conserved quantity is inevitable.
That sounds incredibly important.
It is, but this relationship is not without its complexities. Remember, even the conservation of energy is violated by the expanding universe, and certain symmetries may not apply to all interactions. I keep thinking about how amazing this world of curiosities is. There's so much to discover and understand. Are you captivated as I am? I'd love to hear your thoughts, listeners. And don't forget, if you're enjoying the content, let us know. I'm thrilled to dive into these wonders of the universe with you. To wrap up our discussion, it's worth highlighting that understanding the fundamental structure of your theory and applying it correctly to the universe can teach you exactly what is and isn't conserved in reality. This is the essence of what we've been talking about today.
It's incredible how we can come to understand the fundamental workings of the universe through these principles.
Indeed. And while these principles may seem abstract, they have real implications for how we perceive and interact with the world around us. They allow us to make sense of complex phenomena and to predict the outcomes of physical interactions. It's truly a testament to the power of human curiosity and ingenuity. So we've delved into the intricate connection between symmetries and conservation laws in physics. These conservation laws are not just empirical observations, they're a consequence of the symmetries exhibited by physical theories. This all leads back to Emmy Noether's revolutionary theorem, which states that for every differentiable symmetry of a physical system, there's a conserved quantity.
It's like a cosmic treasure hunt. The symmetries are the map, and the conserved quantities are the treasure.
That's a great way to put it, Sonia. But remember, we have to be careful not to impose additional symmetries or conservation laws that may not actually exist in nature, like the expanding universe violating the conservation of energy. Knowledge isn't just about knowing, it's about understanding.
Absolutely, Caesar. And with that, we're nearing the end of this fascinating journey. We hope you've enjoyed this trip in the world of symmetries and conservation's laws as much as we did. If you did, don't forget to blast that like button and share this episode with your friends. And remember to keep your curiosity alive, because who knows where it will lead you.
That's right, Sonia. Thanks to all our listeners for joining us today. We'll see you in our next episode of Curiosity Wonderland, where we'll explore yet another curiosity. Until then, keep wondering, keep exploring, and keep discovering.
Goodbye, everyone. Stay curious and keep exploring.
This intriguing information was found on the Big Think site in an article titled Ask Ethan, How Do Symmetries Lead to Conservation Laws?, penned by Ethan Siegel and published on March 29, 2024. You can find the full URL in the video description if you wish to delve deeper into the subject. Now, I'll be signing off.